Okay, and so this deals with mean, but something we call weighted means, which an example would be your grade point average, um, in terms of how you calculate it. So that sorry. In this case, would appear that an A gives what we call 4 points, an A minus 3.7, a B plus 3.4, a B is 3, a B minus 2.7, a C plus 2.4, and a C is 2.0. Now, your GPA, like at WVUP, we don't differentiate A minus, or B plus, B. Hey, don't meow me. Attacking like a tar. And it's straight. A is 4, B is 3, C is 2, D is 1, F is 0. Now, so let's say, for an example, and this is number, I believe, 20, last problem. You're looking at 6A. Hold on a second. Oh my gosh. So, looks like we're going to have grades of, now the list class of statistics, Eastern religions, French geology, geology lab. So I'm not going to write all that. What I am going to write is the number of credits or credit hours each course has. So, which will be 4. So that was statistics. This was the Eastern religions. French is just 3. Geology is 3. And the geology lab is 1. So like our course is 3 credits. And then the grade for each course is going to be a B minus, a B, a C in French, an A minus in geology, and a B in the geology lab. Okay. So the weight, this is where we're going to come up with our weighted mean. So B minus was 2.7. And B was 3. We'll say 3.0. For the C is 2, so 2.0. A minus 3.7. And then the B has, again, a weight of 3.0. Now, and so this is where the weighting is going to come in. So these courses were 4 credits. These were 3. That is 1. So this is going to be the credits times the weight. And so that will be 4 times 2.7. This will be 4 times 3.0. 3 then times 2.0. 3 times 3.7. And 1 times 3.0. So for like us here at WVUP, you can we don't differentiate with minuses and pluses. So it was, for this course, if you get an A, it's going to be a 3 times 4. And so your credit times weight would be 12. for us. All right, so if you go through and do the multiplication, in each case, 4 times 2.7 is 10.8. 4 times 3 is 12, and rounding at tens place, or writing tens place here. This would be 6, 3 times 2, 6.0. 3 times 3.7 would be 11.1. And then 1 times 3 is 3, so 3.0. Now, to actually find your GPA, you're going to add all your weighted scores, when that was, again, credits times weight, and add all that up. So adding this column right here is going to be 42.9. And then, where we would, we talk about mean is just adding up all the data and then dividing by the number of data values. So for weighted mean, you're going to, again, weight your grades by their whatever the established weight is, then times that number of credits. But if you add up your credit column, you're going to have 8, and 6 is 14, plus 1 is 15. So you're going to have 42.9 divided by 15. And that's going to come out to be 2.86. And so that would be your GPA for that semester. All right, any questions on finding GPA? Now, again, yes.
I think I'm okay.
Okay.
Thank you.
Yep. So again, at WVP, it would just, you wouldn't have you would either have 4, 3, 2, 1, or 0, but you would multiply, our weights times the number of credits, add that up, and then divide by how many credit hours you took in that semester, and that would establish your GPA. Your overall GPA is all credits times weights for all, every semester times all of your credits. Okay. So there's a second question, and it is, what grade would the student need to earn in French to raise her GPA over 3.5? Okay. So what this is going to end up doing, it's a little bit of, oh shoot. What we're going to do, so this was actually part just A. I'm going to go ahead and turn the page. Part B. And now we want to know, student had earned a C in French previously. So assuming we have those same credit times weight, and French is going to be 3 hours, and we know what GPA we want, 3.05. It's going to end up being what we call a little linear equation. We're going to solve for a variable, but knowing that we add up all those credit times weights, which was, they were 10.8. And then we had 12. And now the French, what I'm going to do is I'm going to introduce, I'm going to say X. And what X is going to be is the French weight. I don't know what that is yet. So I'm going to bounce back real quick. In this problem, it was 6. And when it was 6, it gave us then 42.9 and then dividing by the 15. So we know we're going to need more than 6 to get this to raise up to 3.05. So I'm just going to say 3 times whatever this value is going to end up being, the French weight. Then we had 11.1. That was what we got out of the geology with the A- at 3 credit hours. And then geology lab was 3.0. Now we're still dividing by 15. Now what we want this time is 3.05. Okay. Now, so on any equation, which is what I have, so I need to figure out what number does this need to be to make this equation true. All right, so I'm going to figure out what value I need in for X to make this work. Now, all of this is being divided by 15. An order of operation says you divide before you multiply. So what I'm going to do is I'm allowed with any equation to multiply both sides by the same thing. So I'm choosing 15. As long as I multiply both sides by the same number, I have what's called an equivalent equation. It'll have the same solution. Now, I'm doing this because on the left side, the 15s cancel. And then I just need to go 3.05 times 15. So what I'll be left with, 10.8 plus 12 plus that 3x plus 11.1 plus 3. And then on this side, 15 times 3.05 is 45.75. Now, these 4 numbers here, I can just add together. And so if I add those all up, that's going to, so 10.8 plus 12.0 plus 11.1 plus 3 is going to add up to be 36.9. And then I got the plus 3x. And then equaling 45.75. All right, so now just the same as I'm allowed to multiply both sides of an equation by the same thing, and I still have an equivalent equation, I can add the same thing to both sides. Or in this case, I want to add the opposite, because what I want to do is I want to get this term by itself. And so what I'm simply going to do is I'm just going to say I'm going to subtract 36.9 both sides. So this is 0, leaving me just it'll be 3x plus 0, which is 3x. Now 45.75 minus 36.9 is 8.85. Now, I can say, and this is like 2 sides of the same coin. You can either say multiply both sides by 1/3, because 1/3 times 3 is 1. And then 1 times x is x. That puts x by itself. A lot of people like to write it this way, say divide by 3. Again, I'm doing the same thing on both sides. And it doesn't matter which way you do that, it's the same exact thing. So I'm going to say just divide both sides by 3. Again, that cancels these out. And then I would just calculate what is 8.85 divided by 3. What that gives me is x, that French weight, the weighted score from the French class that I would need to get that GPA to be 3.05 is 2.95. Okay. All right. So now, when going back to those weighted grades, since there are none of them in this, it'd be the same for us because we just have 4, 3, 2, 1, 0. None of them are going to give you exactly 2.95. So in this case, a B minus is 2.7. That's not enough. And B plus is 3.4, but a B is 3, which is more than 2.95. So at the end of the day, the student would need to not get a C, but get a B. And then you would actually be a little bit more than 3.05. So so you would need, again, in this case, a B. Let's make sure there wasn't any other questions. That's it. So student would need to earn a B at minimum. So if they got a B plus or an A, it's certainly you're going to exceed the 3.05. All right. Does that help? Or any questions on part B?
No, I think I'm okay.
Okay.
I'm good. Thank you for that.
Okay, you're welcome. Any other questions from 6A? If not, I'll go ahead and I'm going to talk about 6B. Now, oh my gosh. I'm sorry, guys. I keep getting up. She's wound up and is a menace to civilized society.
Can you hear me good on your side?
So yeah, she was trying to play my guitar there a little bit ago, and then she got up on top of something and started knocking stuff off. All right, so we're going to look at 6B. So 6A, again, we were looking at what the book didn't phrase it this way, but it's measures of central tendency, finding the middle. And we looked at mean, median, and mode in terms of establishing the middle of a distribution. So what we're going to be focusing on tonight is looking at variation in a data set, in a distribution. Okay, so I'm going to look at an example and why variation is important. So let's say we've got a bank, and one bank is called Big Bank. And we got another bank, and it's called Best Bank. So by the naming of, in our little hypothetical example, Best Bank is probably going to be better than Big Bank. Now, what we've got here are wait times. So you go to the bank and you got to get in line to see a teller to do something. And so these are the wait times in minutes for 11 customers at each bank. So I've got 11 pieces of data for each. And again, these are wait times. So I've got 4.1, 5.2, 5.6, 6.2, 6.7, 7.2, 7.7, 7.7, 8.5, 9.3, and 11 minutes for this other customer. They had to wait. So, and if you're waiting in line, standing, there's a big difference between 4 minutes and 11 minutes. A minute's going to seem like an eternity when you're waiting in line. If you're like me, I have no patience waiting in line. Now, Best Bank, these 11 customers, shortest wait was 6.6. So that's more than the shortest least time for Big Bank. But 6.7, 6.7, 6.9, 7.1, 7.2, 7.3, 7.4, 7.7, 7.8, 7.8. All right. So here's the deal. If I were to look at the median, now remember, median is arrange your data values from least to greatest in ascending order, and then find the middle. Now it's 11, so it's an odd number of data. So you're going to hit a middle, and that middle for both, notice, is 7.2. So the median for both of these is 7.2. The middle is the same in terms of median. Well, and this problem was kind of cooked up a little bit on purpose, these numbers. If I would calculate the mean, in this case, the mean for both is 7.2 minutes, meaning if I add up all the data values and divide by 11 in each case, I'm going to get 7.2 minutes. So the middle was exactly the same. But there's definitely, if I look at how spread out the data is, it is much more spread out in Big Bank. It goes from, smallest value of 4.1 minutes and the largest value of 11 minutes. And Best Bank is 6.6 minutes, all the way up to 7.8 minutes. So now, and so, what is the deal? What is the, why do we have this difference in variation? At Big Bank, there are 3 lines. So a customer comes in and they're going to choose, one of 3 lines, and they jump in one of those 3 lines. And so what happens is some lines move faster than others. And so, and I think we probably all, I know I have had this experience. I like to think the grocery store, was really busy. And so like you're at Walmart or something, and you got 3-4 lines there to choose from. You try to look, if you're like me, you try to look and find the one you think is going to move fastest, but it's always a gamble. And then all of a sudden, the cash register breaks down, or computer goes crazy, or there's a problem, there's some sort of problem. And next thing you know, you're watching people who came and got in line after you, and they actually check out before you. And so it leads to frustration. So the deal with Best Bank is there's just 1 line and 3 tellers. And so, and which is what basically happens is probably there's a little bit less frustration at Best Bank in this situation, simply because the times are so compacted around that middle. It all seems fair. So, but it's a good example of looking at why variation is important. So what we're going to look at is different ways to measure variation or look at variation in data. And the first is what we call, the simplest, range. And range is simply your maximum data value, your maximum value minus your minimum value. That's all it is. So, you know, in the case of, and then, you know, for this one, it gives you a good idea of there is a lot more variation in the two banks. The range of big bank in this case would be 11 minutes minus the 4.1 minutes, which is 6.9 minutes. And the range of best bank would then be 7.8 minutes minus 6.6, and it's significantly less. It's just 1.2 minutes. Okay. Now, so it does, in this particular example, looking at range does give you a pretty quick indication that one data set has much more variation, even though the middle was the same. But that range can be very misleading, which is why we're going to need some other ways to measure variation. So as an example of where range can be misleading, let's say we have some quiz scores. And we got quiz 1 and we got quiz 2. So these are just going to be quiz scores. And quiz 1, student scored a 1 out of 10, but everybody else scored a 10. And it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 data values total. So 10, 10, 10, 10, 10, 10, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I think I got them all there. Yeah. Now, the scores of quiz 2 were 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Now, so the range here would be 9, because it's going to be 10 minus 1 is 9. The range here is going to be 10 minus 2, which is what? 8. So if you compare this to, you'd say not a lot of what? Variation there, or excuse me, not a lot of difference between the two, but I think it's fairly obvious if you look at the two. Quiz 2 has a lot more variation. As a matter of fact, if you consider this to be an outlier, because it is, it's way different than any of the other 8 scores, then there's like no variation if you exclude that. If you exclude this, because then all the scores are 10. Where here we definitely, you know, they're much more spread out, but the range would not really give you that indication. So, so what that sets up, and again, it just shows range. It's a simple way to calculate. It's easy to calculate, but it can definitely be misleading in terms of how much variation there is within a data set. So A couple other ways we're going to look at variation. The first one is going to be based on median, and then the second way is going to be based on mean. So, first one, and I want to go back to our best bank and big bank setup. So I've got big bank. And I've got best bank. All right, so big bank. Got 4.1. Got to write all these scores again. Wish I could do a cut and paste. 5.2. 5.6. 6.2. 6.7. 7.2. 7.7. 7.7. 8.5. 9.3. 11.0. And then the best bank times 6.6. 6.7. 6.7. 6.9. 7.1. 7.2. 7.3. 7.4. 7.7. 7.8. 7.8. All right. Now, we already know 7.2 was the median, and for both. Okay, now what I want to do, I think I can make this work. There we go. So contrast, go red. So right here, these two scores was the median. All right. And I'm gonna, you don't have to erase it in your notes there. What I'm gonna do, I want to give myself a little bit more room. So the 7.2s were the median. Now what I'm going to do, if it's an odd data set, then that divided this into what, 5, and then an upper 5. That lower 5, I'm going to find the median of the lower 5 pieces of data in each case. And that median of the lower 5, I'm going to call the lower quartile. And then I'm going to do the same thing for the upper 5, which would be right here. And it's the median of these 5. And then I'm going to call that the upper quartile. Okay. Now, so at the end of the day, and then I could literally have what I call the lower quartile, the middle quartile, or the second quartile. Sometimes this is also referred to as the first quartile. This is the second quartile. This is the third quartile, or lower quartile, median, or the middle quartile, and then the upper quartile or the third quartile. Now, so if it's an odd data set, you're going to exclude that. Now, if it's an even data set, then you know to find the median, you find the two middle pieces. And so then from there, you'll split it And that will give you actually at that point. So let's say hypothetically, we had another data value here and gave me at 12 data points, then these two would have been, find the average of those two for the median. And then you would take the lower middle piece and then all those data values and find the middle and do the same thing for the upper. But this is going to give me what I call, I'm going to go back and change my color. Went up blue. What I'm going to call my 5-number summary. So I'm going to get 5 numbers out of here. And they're going to be lowest value, lower quartile or first quartile, the median, upper quartile, or third quartile, and then your highest value, the maximum value. Okay. So, so in this case, for big bank, and then for best bank, then looking at the 5-number summary, big bank, lowest value was 4.1. Your lower quartile was 5.6. The median was 7.2. The upper quartile would be 8.5. And then your highest value was 11.0. Best bank, your lowest was 6.6. Your lower quartile was, or the first quartile was 6.7. Your median was 7.2. Your upper quartile or third quartile was 7.7. And then your highest value was 7.8. But again, the 5-number summary are those 5 values: your minimum or your lowest value, the lower quartile, the median, the upper quartile, and then your maximum value or highest value. Now, looking at the numbers, I mean, just looking at this, I can tell there's more variation here than there is here, but there is a visual way to display it, and then it's like really obvious. And so I'm going to turn the page. And I want to show a visual display of using those 5 numbers, a 5-number summary. So now, so I'm going to draw a little graph like that. This a horizontal axis. But on this, I'm going to have a big bank here. And best bank here. Okay. Then remember, these were wait times in this example. So I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right. And then I will label my horizontal. Again, these were waiting times. Okay, in minutes was the unit. Now, so here's 7. 7.2 is the median. I'm going to do Big Bang first. So I'm going to put a line right here. That was 7.2. And it doesn't need to be bolded like that. It's best estimate, visually where it looks like it's 7.2. All right. A little bit longer. All right. Now I'm going to go to, for Big Bang, the upper quartile, third quartile was 8.5. So that would be halfway between these two. So it's about right there. And the lower quartile was 5.6. So that would be roughly about right there. Right. Now, the minimum value was 4.1. So that's down about right there. And your upper value was 11. So that's right there. Then what I do is from the lower quartile to the upper quartile and the median, I connect like this. So I make a box. And then I make a line from the upper quartile up to the max value. And then I do that. All right. Then Best Bank, I'm going to do exactly the same thing. I'm going to put in the median, which was 7.2. So it's going to be exactly right there. But the upper quartile was 7.7. So that's about right, roughly there. And the lower quartile was 6.7. So it's a little bit more than 6.5. So it's about right there. The minimum value, or the lowest value, was 6.6. So that's right there. And the highest value was 7.8. So that's right there. And then I'm going to do the same thing. I'm going to connect up the lower quartile and the upper quartile through the median. And then I'll do that. Now, visually, now it's really obvious which one has more variation. And typically, we always actually would put these values in 4.1 and 5.6 and 7.2, 8.5, and 11.0. And then I would do the same here. As neatly as I can. I'd have 6.6 and then 6.7, 7.2, and 7.7, and then 7.8. But it really shows the variation difference for sure. Now, your book calls this a box plot. I learned it as something else. So an alternative name for this kind of graphical display is, and this is my preference, it's called a box and whisker diagram. And I think box and then the whiskers, going from the upper quartile to the maximum value, and then the lower quartile down to the minimum value. All right. Any questions on this? And you can find them where they will, when your book does it, it'll actually connect right through here. That's optional as far as, because I didn't learn it that way. But so, any questions on a box plot, or what I call box and whisker diagram?
I don't think so. The way that you did it is how I learned in, like, I don't know, I think it was like my junior or senior year.
Okay.
Yeah.
So you've seen them before.
Yeah.
Okay. And so just again, it gives you a really good visual way to measure or look at the variation difference, and it's based on median. And so, and I can see within and it's called quartiles because it's 1, 2, 3, and 4. And so I can visually see, from, what I call this quartile right in here, there's certainly more variation than really anywhere else. It's in like here in this lower part for the best bank, there's very little variation in the data. Okay. Now, so what would be nice though, and incidentally, you can take this idea of quartiles and go with what are called deciles. And so you're not chopping it up into fours, you're chopping it up into 10 sections or percentiles, and then it's 100. That's usually how standardized tests are measured in terms of you always want to be in that 99th percentile when you take a test, because then you're on the very upper end. But what would be nice if there was a way I could look at variation with one number. That's it, just to calculate one number. And then based on that number, I would get a good sense of how much variation was in the data. And there is, in fact, a way to do that. And it is called standard deviation. Now, this is based on the mean. Basically, what it's going to give me is this number is kind of going to give me an average of how much the data deviates from the mean, from the middle, in the case of arithmetic average. So now calculating it can be a little bit of a pain. If you're a statistician, there's high-powered software out there which will do all this grungy arithmetic for you. It's programmed to go through this. So when we talk about a deviation from the mean, okay. So remember back to our best bank, big bank example. The mean was what, 7.2. It was that the median was 7.2 minutes and the mean was 7.2 minutes. So if I looked at a waiting time of like 8.2 minutes, then I could say I went 8.2 minus that 7.2. That would give me 1. And 8.2 then has a deviation from the mean of 1 minute. Okay. Now, so now, if you're like, say, 5.2, then if I were to consider, your wait time was 5.2 minutes, then that would be 5.2 minus 7.2, which would be negative 2.0. So 5.2 has a deviation from the mean of negative 2.0 minutes. Okay. So when we look at standard deviation, right, itself, it's an average of the sizes of so you could go through each and every piece of data you have in your distribution and find each individually what its deviation from the mean was, all of them. And so standard deviation is going to kind of give you an average of all of these sizes. Okay. So, and again, it's going to give me one number. All right. All right. So calculating standard deviation. How are we going to go about calculating it? So turn the page. Try that again. All right. It is multiple steps. All right. So step one. First thing we want to do is calculate the mean. So find the mean of the data set. Find a data set. Add up all the data values, divide by the number of data values. Okay. And then find deviation from the mean for every data value. Okay. So that's where I was going, what? Data value minus mean. So I'm going to put parentheses here, and we did a couple examples of that. So the deviation from mean is data value minus the mean. So it's always that order. All right. Now, a little bit of an issue. If I were just to then find the deviation from the mean for every single data value and then add that up, I'm going to end up with 0. Because because you're finding that arithmetic average, so half of them are going to be negative and half of them are going to be positive, and what's ultimately going to happen is, again, it's going to add to be 0, and that's not going to give me any information at all. So what I'm going to do to take care of those negative deviations from the mean, so those data values that were smaller than the mean, I'm going to square every single data value, if you multiply a number by its times itself, the result's going to be positive in every case. So I'm going to then square every deviation from mean, so that I'm not going to run into that problem of adding them all up and getting 0. Right? So I'm going to put IE, raise them to a power of 2. All right. So number 3. Now I'm going to add it all up. So I'm going to add up all the squares of deviations from mean. All right. Number 4. Now, I'm going to divide the sum of step 3 by the number of data values minus 1. That is add up all the, how many ever data values you have and take away 1 from that. So in our big bank, best bank scenario, there were 11 data values. So you'd be dividing by 10. Okay. All right. Now it's a little hard to explain why you go minus 1. And explaining that, but it has to do with the fact that usually we are looking at a sample, not the entire population, and it gives a better result is all I could really say. But that is what you want to do in this particular case. Now, the standard deviation, we're finally at the last step. The standard deviation is this, and because we had squared everything in that second step, to undo that, I'm now going to take its square root. So the standard deviation is the square root of the quotient. It's a result of the division where I divided the squares, the sum of the squares of the deviations of the mean by the number of data values minus 1, and then take that number for number 4 and take its square root. So the standard deviation is the square root of the quotient found in step 4. Okay. Now, so I'm going to write this up in a little bit of a formula. We're going to say standard deviation is, now it's a square root. And remember from Tuesday, sigma means add up everything. Well, what was I adding up? Remember, it was the data value minus the mean. Remember, I represented mean with that X bar, and then I squared every one of them. And then this indicates add them all up, then divide by the number of data values, which would be n minus 1. So that's officially the formula that you would find in any statistical book for standard deviation. So now, just so we're aware, this can be, if you do this by hand, it's time consuming. because you've got to go through and find the deviation of the mean. So depending on the size of the data set, for 11 data values, that's still going to take a little while. You're going to have to find the mean, which was 7.2, then go every single data value minus 7.2, then take all of those and square every one of them, and then add them all up. Now, if we would do that, incidentally, big bank, best bank. So if you would go through and find the deviation from the mean for every single value, and then square every one of those, and then add them all up for big bank, you're going to get 38.46. Now remember, we then divide by the number of data values, which was 11 minus 1. So we divide by 10. So that gives me 3.846. Best bank, finding the deviation from the mean for every single data value, and then squaring every one of them, and then adding them up, you get just 1.98. And then it also had 11 data values, so then divided by 10, and that gives me 0.198. Then the standard deviation is the square root of that number. So the standard deviation of big bank would be the square root of 3.846, which then rounded to hundreds place is 1.96 minutes. And the standard deviation for best bank is 0.198. And so the square root of that rounded is roughly 0.44 minutes. Okay. So the bigger the number, the bigger that standard deviation, the more variation in the data. So then you can compare the two, and then we already knew there was more variation at the big bank waiting times than the best bank waiting times. And it's reflected in, again, the standard deviation. Now, standard deviation then gets used for establishing all kinds of other things in terms of interpreting data. But this is just all we're really wanting to concentrate on right now, is finding the standard deviation, and then realizing what that number tells me. Again, it gives me a kind of an average of the deviations from the mean for all the data values. And then the bigger the number we get, the more variation there is. But like I said, we can go on and actually establish that, given any data set, if we have a normal distribution, that bell-shaped curve, that at least 75% of the data will lie within one standard deviation, and at least to either side of the mean, and at least remember it's wanting to say 90 some odd percent is within two standard deviations, and almost 99% of the data will be within 3 standard deviations. So one other thing, there is a way to estimate standard deviation. and it's called the range rule of thumb. Okay. So if I want to approximate a standard deviation using this range rule of thumb, it's approximately the range, which is easy to calculate. Again, that's highest value minus lowest value, max minus min, divided by 4. Okay. All right. And if we and if you know the standard deviation of a data set, you can estimate the lowest and the highest values. And this is to say that's all you know is the standard deviation. You don't actually know what the data set is. You can estimate what the highest and lowest values is. This is basically then, estimating the range, because all you know is the standard deviation. Your lowest value, if all you know is the standard deviation, is approximately the mean minus 2 times that standard deviation. I'm going to abbreviate that. And the highest value, so you've got to know the mean as well. The mean plus 2 times standard deviation. Now the reason again is for that. A lot of times we assume a normal distribution, is most of the data has to lie within 2 standard deviations. Now, if the highest or lowest value is an outlier, then your estimate may not, again, it's just an estimate, so it may be off, a good bit. And then kind of just looking at back to Best Bank, this was the standard deviation calculator for Big Bank, 1.96. Well, Big Bank had a range of 6.9, and 6.9 divided by 5 is about 1.7. Yeah, it's a little bit less, but it's kind of in the ballpark. And 1.2, which was the range for Best Bank, this was Big Bank, divided by 4 is about 0.3, which again is a little bit less than this, but it's in the ballpark. So, all right. And that takes us through everything we need in 6B. 6C, and I don't think I want to do 6D. I'm undecided about that one. Yeah, probably what I'm looking at doing, and I'm going to go ahead and give me a second.